Every day, the future's getting closer.
Welcome to Master the NEC, where we talk about the National Electrical Code and all things electrically related. My name is Paul Abernathy, your host, and welcome to today's podcast. Well, hello everybody. Welcome to another episode of Master the NEC, where we talk about the National Electrical Code and all things electrically related. Well, you're in a treat today. Today we are going to talk paralleling conductors. We're going to talk about some of the problems that are associated with improper paralleling, and we're going to go over the principles that are pretty set in stone when it comes to the National Electrical Code when you're doing a parallel conductor installation. And we'll talk about what can go wrong if you don't know how to properly follow all of the requirements for paralleling. Now, look, many of you have probably paralleled and you install it and nothing ever goes wrong. And you're like, hey, paralleling's easy. Well, the problem is with paralleling is up front, the loads might not be there to create an issue. But down the road, when your demand becomes increased, and if you don't do paralleling properly, then you don't have an even proportional distribution of current on each one of the actual phase conductors. That can be a problem. So at the end of the day, it's really important to understand paralleling and how to apply the rules of paralleling. Now, in most commercial buildings, when you're getting in services that tend to be over 400 amperes and higher, typically you're going to have 3, 4, even 5 sets of parallel conductors, and that's parallel. That means you're going to have a number of sets of conductors per phase that you're going to have to deal with. Now, why do we even do it? Well, economically and practicality is that it's much harder to run larger conductors. Raceway sizes are going to prohibit you from installing conductors of large size in raceways. It just becomes a lot harder to work with. Bending issues becomes a problem. It's just more difficult to install. So typically when you start getting over 500 kc mil, most people will start looking at paralleling. Okay, so that's kind of what we want to cover. We want to talk about all of the rules that are going to be really something you need to know about that are found in the National Electrical Code. Most notably, we're going to be dealing in 310.10H. That's the area in the code that talks about the characteristics of paralleling and what you have to make sure that it happens properly in order to be able to make sure you're not going to screw something up. So we're going to cover all those things and give you good parameters of understanding paralleling and how that applies. But we're also going to talk about the problems that can happen when you don't take these things into consideration. And I think that's the real topic of today's show, is that so many people will parallel, but they don't understand the concepts behind it and all of the nuances that need to be maintained. I can tell you right now, as a expert for a wire and cable manufacturer, if something happens and an insulation melts down, let's say it's a thermoplastic insulation, which is a malleable insulation when you get to a certain temperature, anytime you start getting over 90 degrees C, as long as the conductor is rated for that, then once you start elevating beyond that, then you have a potential to break down that insulating material. So that's why we do so many adjustments and corrections in order to keep that temperature down, so that we don't exceed the rating of the conductor's insulation, because that's its lifeline, right? That's its protection between the outside influences like metal raceways. It could cause a short in that inner conductive material. So what we're going to do today is look at all the little nuances that are involved in paralleling, because a lot of times I've been called out on jobs where somebody claims something happened or meltdown, and you know what? If I'm the kind of guy that gets called out there for an issue where it looks like conductors had a problem and I find out you didn't parallel it right and it caused a problem of putting distribution of current on the multiple sets that you're dealing with, and ultimately one set had more current traveling on it than the other because it didn't divide proportionally, then probably you're going to lose. And I'm going to be ready whenever we go to court because I'm going to keep all my ducks in a row. And that's what I do. That's my job. That's what I do for the company that I work for. And as a consultant, I will pick through the engineers and look for mistakes, look for things they might have done wrong, and I will exploit those. And so if you're dealing with paralleling, they're really simple if you follow the basic parameters, and we're going to go over that today. Okay. All right, so before we even get started in that, I want to make sure you know what edition of the National Electrical Code we are in. We are in the 2017 edition of the National Electrical Code. We are on the softbound edition, I guess the code book, the soft one. That is page 146, and in the electronic digital version PDF, it is page 149. So, guys, gals, if you're ready to do this episode, go get your code book. It might be on the dashboard of your truck, the one that's all faded out now because you hadn't looked at it in a long time. Or maybe it's in your desk drawer, or who knows where it is. Get it out, blow the dust off of it, crack it open, and let's go on and do some learning today. All right, why would I ever want to parallel conductors? Let's start there first. Well, again, I could have issues in most commercial buildings where I'm going to have a situation where I'm going to probably have over 400 amps where paralleling probably is going to come into play. And once I start getting to about 500 kcmil and larger, it's just more difficult to install, more difficult to bend. Its raceway limitations are going to make it so that you can't put larger conductors in it, and it just becomes more difficult. So being able to utilize the allowances of paralleling really makes your job easier, okay? Again, I can get larger amounts of current evenly distributed across multiple sets of conductors and still achieve what I'm trying to achieve. And that's the whole concept of paralleling. But we want to make sure that the current evenly divides amongst the phase sets. Okay, so there are some rules that we have to follow. First things first, I usually tell people, crack open that code book and let's go to 310.10H1, and we're going to look at some general requirements. So these are general, broad requirements that we're looking at when it comes to being able to phase conductors and the limitations in size and how a phasing, a parallel of phasing effect takes place. First of all, it says 310.10H1, general. It says aluminum, copper-clad aluminum, or copper conductors. Okay, all three of these conductive materials are acceptable in a paralleling application. It says for each phase, polarity, neutral, or grounded circuit shall be permitted to be connected in parallel. Okay, now, then it has in parentheses, electrically joined at both ends. Okay, so typically, if we're doing feeder at one end and then at the other end, they're identically, all the sets, individual sets are identically terminated. Okay, like all phase A's, all phase B's, all phase C's are all terminated identical to that phasing branch. Okay, and I use that term loosely. So, one of the things to remember is we have size limitations. Okay, it also reminds us that in paralleling, if we continue on, it says only in sizes 1/0 AWG and larger were installed in accordance with 310.10H2 through H6. Okay, so we're going to look at H2 through H6 and make sure that we understand that there's paralleling requirements, again, electrically joined at both ends. And of course, we're going to also look at the sizing, minimum sizing, as well as some of the characteristics and installation stuff that we have to look at here in order to make sure we're doing our install properly. Okay. Now, there's some exceptions to this rule when it deals with the 1/0 in size. And basically, exception number one are dealing with conductors smaller than 1/0 are permitted when run in parallel with supply control power to instruments, contactors, relays, solenoids, and similar, which I'm not going to get into. Also in frequencies of 360 hertz and higher, provided you meet all these requirements. We're not going to touch those. I'll let the engineers sort those out if they want to do an application where they expect the paralleling of any of these phase or neutral or grounded conductors to actually be smaller than 1/0. I'll let them worry about that. Otherwise, I'm not going to get into that exception. And of course, exception number 2 is under engineering supervision. That means that an engineer will specify out smaller, and they're going to allow to do it for an existing installation or something like that. Again, that is going to be under engineering supervision, and I am not a licensed PE in any state, so I am not getting into that. But your PEs, if they for some reason want to parallel smaller than 1/0 and they do it, then they have an exception they can look at, and that might give them some guidance. Okay? All right. And again, that is really for existing buildings where they might have some issue with harmonic currents or whatnot, and they'll get to utilize exception number 2. Again, we're not going to talk about that in this program. We're going to talk about what you need to know, what might be on an exam, in real practical, real-world scenarios. Okay? All right. Next is 310.10H2. It says conductor and installation characteristics. Now, 310.10H sets forth the requirements for installing parallel. The requirements are intended to ensure that conductors will share current equally. The reason we're doing this is to prevent overheating on any one individual conductor. Okay? So, what do we have to do? All right, well, they have to be 1 aught and larger. They have to be the same length. Okay? And we're talking about the parallel conductors of the set, of each individual set, like A's, B's, and C's. Okay? I'll explain that in more detail in a minute. They need to be of the same material. In other words, copper to copper or aluminum to aluminum. Okay, so I could have all phase A copper, all phase B aluminum, all phase C copper. Okay, but of the phases, they have to be the same characteristics as far as same material. The next is have the same insulation type. So all phase A would have, let's say, THHN. All phase B could be X. I'm just saying for each set or phase, they have to be the same. Next is you have to have the same size in circular mill. So all of phase A circular mills have to be the same size, all B same size, all C same size, okay? If they're all the same copper material, then that's a no-brainer, then they'll all be the same size in order to distribute out evenly, okay? So I'll just keep that in mind. And then lastly, each terminate in the same manner, okay? So they have to terminate whether they're on set, screw, lug, whatever the lugs are, the termination has to be done in the same manner. Okay? All right? And again, remind you that when we're reading all these rules, the code actually says this, and I'll read it to you. It says the parallel conductors in each phase. In each phase. Polarity, the neutrals, grounded circuit conductors, equipment grounding conductors, or equipment bonding jumpers shall comply with all the following. So, parallel conductors in each phase. So, all of the A's have to comply with these rules, all of the B have to comply with these rules, all of the C have to comply with all these rules. And then a lot of times when people see the one that talks about the same size in circular mill, do they mean that A can be one size, B can be another? So, say A is copper and B is aluminum. Well, aluminum conductors are going to have to be larger to carry the same amount of current. So obviously, all of the circular mill area of those conductors in B phase are going to have to be adequate, one, to handle the current equivalent to what would be on phase A or phase C if those were copper. But it does mean they might be larger, but as long as all the conductors are larger than in that phase, then they're okay. They all have to be the same circular mill for that phase. All right? If you're running neutrals, all the neutrals have to be the same. Okay? Same size, same insulation type, all that. Same length, all that good stuff. Okay? All right, so the raceway or cables are required to have the same electrical characteristics as well. For example, if I'm running a raceway and I'm running 3 parallel runs, don't use schedule 80 PVC on one raceway, and aluminum for another, and steel for another. Okay? That typically would not be something that we would have done. It's critical that the conductors be the same length. And so that's just something to keep in mind. It doesn't really make sense to break up and do that as far as your characteristics. Why? Because it goes on in item number 3, and that's 310.10H3, that reminds us, and here's where we get this from. Whereas we're a little different with the conductor characteristics, when it's separate cables or raceways, the code specifically tells me, it says, we're running separate cables or raceways, obviously we're paralleling it, which you could do all in one raceway, but really it would be probably a big raceway when you think about the benefits of paralleling. It's only really done when you get really larger conductors, so you're going to have multiple raceways. So this is going to apply. It says, again, we're running separate cables or raceways. The cables or raceways with conductors shall have the same number of conductors and shall have the same electrical characteristics. Conductors of one phase, polarity, neutral, grounded circuit conductor, or equipment grounded conductor, shall not be required to have the same physical characteristics of those in another phase. Okay, so we kind of clarified it. Okay, but the raceways, okay, shall have the same number of conductors and shall have the same electrical characteristics for each one of the raceways. So, yes, I can parallel MCs, MC cables, metal clad. Yes, I could parallel EMTs, but we want to keep, when we do parallel, while the conductors are based on the characteristics of each phase, the actual raceways or cable have to be very much the same, even if you parallel them in multiples. One thing to remember, just as a note, when you're paralleling MC cables, for example, a lot of times those cables come already made. So what happens is you have an issue where the equipment grounded conductor inside of the MCs might not be adequately sized because you're paralleling MCs, and then of course the overcurrent device on the supply side pushes you towards selection of an equipment grounded conductor in 250.122. Well, that could result in you having to purchase specially made MC. Now, we did add some allowances for that in the 2017 code, okay, when you're dealing with that. So, just understand that you do have some additional allowances for things like cable trays and so forth. Just remember that's the basic rule, basic characteristics that we're working with, okay? All right. Next thing we want to remember, and again, as we move through this type of thing, that when we're talking about ampacity adjustments, conductors installed in parallel shall comply with the provisions of 310.15b3a. And we all remember what that is, right? I hope you do, because that's when you're dealing with more than 3 current carrying conductors, okay, in each raceway. All right, so if you don't know a lot about the adjustment and corrections and things like that, and you're just really lost when we say, okay, I get it. If I have more than 3 or blah, blah, where do I learn more about that? Well, go to our website, click on the link to our YouTube channel. Again, our website is masterthenec.com, shameless plug time. Go to the website, and up at the top, you'll see a link to our YouTube channel. Go to the YouTube channel, click on the videos, and kind of scroll down. You'll see a video called Derating Demystified. Watch that video, because in that video, it talks about how to apply adjustment and corrections for conductors. Because again, based on the adjustment factors or correction factors for ambience, temperatures, and things like that, it's going to change the ampacity of your conductors. And those things have to be taken into consideration. Most certainly, if you're dealing with more than 3 current carrying conductors, you better know how to do it. Okay? All right. So those are all the things that we want to remember when we're running parallels. And then lastly, we'll kind of go down to, let's talk about that equipment grounding conductor that we just talked about. Kind of said that was included with the requirements. But here's what it says. And we're at 310.10H5 now. And this is specifically titled equipment grounded conductors. It says, where paralleled equipment grounded conductors are used, again, sometimes people forget that an EMT, for example, you would be allowed to use the actual raceway, that tubing, as an equipment grounded conductor in accordance with 250.118. I know some engineers don't like that. And in me as a wire and cable guy, I'd much prefer you put a wire in there. But at the end of the day, you can use the NEC to your benefit. It is still going to be a safe installation. People worry about those connections. Again, you're required to install things in a workmanlike manner, and you have to install all the connectors and fittings and meet all the requirements of providing an effective ground fault current path under Article 250. So we're going to assume you do all that. We're going to assume you use proper listed and fittings and all that type of thing. And if that's the case, then you might not have a wire type equipment grounded conductor. Okay, and there's no sizing requirement for raceways, obviously, when it comes to EGCs. But when it comes to the wire, you do. So let's kind of read on in this a little bit further. It says, where paralleled equipment grounded conductors are used, okay, they shall be sized in accordance with 250.122. Again, we talked about that a little earlier briefly. That's where you have the overcurrent protective device dictates the size of the equipment grounded conductor, okay? All right, and that also has to be full-sized in all raceways, okay? All raceways, unless, of course, you're not running one because you're using the raceway itself, provided you can do that. Now, with MC, for example, you can't use the raceway. That's why it comes with an equipment ground in there, okay? But EMT, rigid, IMC, that type of application, then you most certainly could use a raceway if you wanted, okay? All right, so we'll just kind of leave that one at that. And lastly, it talks about bonding jumpers where paralleling equipment bonding jumpers or supply-side bonding jumpers are installed in raceways, okay? It says they shall be sized and installed in accordance with 250.102, okay? So 250.102 talks about how to size the supply-side bonding jumpers and equipment bonding jumpers, and I actually have a video out as well on supply-side service bonding. So again, I'm going to direct you, because I don't want to take away from our paralleling conversation, I'm going to send you to go watch that video over on our YouTube channel. Simply go to masterthenec.com, go up, click on the YouTube link, and that'll send you over, and search for it, and you can find our video on that. Now, you're going to find a bunch of podcasts and a bunch of videos there. In fact, our podcasts are like this, is carried on a lot of other channels. But I always put a copy of all podcasts up on our YouTube, so it's just another way for you to be able to get there and listen if that's the platform you like to listen on. Okay? All right. So let's talk about scenarios, and let's apply some actual issues that sometimes come up. Now I'm going to read you a known issue, and it comes up a lot, and it actually comes out of a book that I'm co-authoring with a dear friend of mine, and it really talks about the scenarios that could happen if you do something wrong. Okay, so in this case, we're going to talk service. That way, we just keep it real. Let's say we have a 1600 amp service, and we have 4 conduits, and each conduit is going to have a 4 600 kc mil THHN. That's thermoplastic. Remember now, in case you didn't listen to some of our other podcasts, T stands for thermoplastic. The 2 H's stand for high heat or 90 degrees C. The N stands for nylon covering. Little tidbit for you. When you're doing an installation, if you're not dealing in an oil and gas environment and you have some of the nylon gets cracked or peeled or damaged, nylon is not considered part of the insulation. It's just a protective membrane. It does lower the coefficient of friction during the installation. It works better with pulling lubricants and things like that. But at the end of the day, in cold climates, sometimes the nylon tends to crack. That doesn't affect the listing of the product or its viability. Again, it's there as a protective membrane, and to be honest with you, it did its job. Now, if you're doing an installation in a known oil and gas environment, then you want to maintain the integrity of that nylon because that's part of the testing. But when we as a manufacturer of wire actually test the THHN and its 90 degrees C properties, we do this, and we do it without the nylon on it because that's what the requirement is under UL 83, and that's the UL's Underwriter Laboratory standard, ANSI UL standard for thermoplastic wire. And so that's how we actually test it. So that kind of shows you the nylon is really sacrificial, but it does help us in the installation process. Unless, of course, you're using gas and oil applications, and it'll be stamped on there PR or GR 1 or 2 or whatever that subsequent rating is. Okay? All right, so it also could have on it what's called a dual rating, so it could be THWN as well. Usually it's going to be THWN-2. But if you just saw THWN on it for some wacky reason, then that tells you there's only 1 H there, so it's okay in a wet location. But it is going to be limited to 75 degrees C tables for ampacity. In fact, if I even had to adjust and correct it, I couldn't use the 90. If it's a wet location, I have to use the 75 because of only 1 H being there. But if it had that -2 on it, then I could treat it just like THHN, and I could start my adjustment and corrections from the 90. Again, if all of that seems foreign to you, then you need to go watch that video on derating demystified. Again, it's about 2 hours long, 2 hours and 6 minutes long maybe of your life you'll never get back, but you might just get some knowledge from it. Okay? All right. So let's look at this. So we're dealing with 4 600 kc mils, THHNs. The allowable ampacity, and again, I'll remind you that the term allowable and maximum is going to disappear from the 2020 NEC. Cats, get ready for that, okay? Because it's really unnecessary. But right now, it's still in there, so we'll talk about it. It says the allowable ampacity of each conductor is 420 amperes, okay? Now, where the service is operating at 1600 amperes, that's what we're dealing with. Really, what we're trying to do is determine, since we're running a parallel set of 4 conductors in each raceway, we want to know what the current is in each of the 4 parallel sets of conductors, okay? Now, let's do it this way. One set is 20 feet long, another set is 21 feet long, another set is 22 feet long, and another set is 23 feet long, okay? So, what we've got is, again, we're wanting to find out what the current is in each of the 4 parallel sets of conductors if their lengths are those various lengths. Okay, now, how do we solve this? Well, the total length of these conductors is 20 feet, 21, 22, and 23. We simply add those together. That's 86 feet. Okay? Now, once we have that total, then we can kind of work it out and see what our conductors and what our ampacity is that we're working out. Okay, now, the current in each set is going to be inversely proportional to the resistance, which is proportional to the conductor's length. Obviously, more length, more resistance. So each one of the conductors will be slightly different. Okay, so remember that. Obviously, more conductive material that current has to travel through, it's going to travel through more resistance. So it's going to be a slightly more resistant into the 21-foot length than it is the 20-foot length, okay? So just keep that in mind. Right now, we're just trying to do some calcs and see what we're dealing with each, based on each length that we're working with, okay? Now, the current length in each conductor in the parallel sets are this. So I've got 20 feet, so 20, and since we dealt with a total of 86, we'll go 20 divided by 86, and we're going to multiply that by 1600, okay? And that gives us a value of 372.09 amperes. Well, I can drop the 0.09. So we're dealing with 372 amperes. So let's take the next one, 21. Okay. All right, so we take the 21 foot divided by 86, and I'm going to do that with you. So 21 divided by 86 equals 0.244186, blah, 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 blah. So on your calculator, do that times 1600. And that gives me 390.69. So we're actually 0.5. We're going to round that up to 391 amperes for that 21. So see a difference here? Just from that 20 feet to the 21 feet, there's a difference in almost 20 amperes. Amazing, isn't it? So next we're going to look at the 22-foot one. So again, do the same thing. Is you'll take the 22 and we're going to divide that by the 86. That was our overall cumulative length. Okay, and that equals 0.25581, blah, 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 blah. You can do that on your own calculator. Okay, and then we multiply that by the 1600 because that's what we're trying to achieve with our 1600 ampere service. Okay, and of course we need conductors that can overall handle 1600 amps at this point because it's over 800 amps. Okay, so that gives us a 409.30 amperes. Well, of course, 0.3 we can drop. It's less than 0.5. So that is 409 amperes on that 22 foot. You see how it's going up? And then lastly, the 23 foot one, obviously, as you've guessed, it's going to be higher ampacity on those conductors, that length. So we're going to take 23 and we're going to divide that by 86, which is our overall cumulative length. Okay, and that's going to give us 0.2674418, blah, 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 times 1600. And that's going to give us 427.9, and obviously that's going to round up to 428. So at the 20 foot, we had 372 amperes being drawn. Those conductors are drawing or can handle. That's basically the current that's going to be on that if we're trying to achieve 1600. And then the 21 foot one is 391, the 22 foot one is 409, and the 23 one is 428. Now, because current is inversely proportional to the resistance, the currents would be 428 for the 20 foot conductor, okay, would be inversely proportional. Then for the 20-foot conductor, and 409 for the 21-foot, 391 for the 22-foot, and 372 for the 23 feet, with only a 1 foot in difference in each set. The current exceeds the rating of one set of the conductors. Okay? So, in one of those sets, you see here, again, it's inversely proportional. So while we did the value, then we turn around and we actually inversely proportion it so that we can see what actually it's really going to be on the shortest one, which is going to take the brunt because it doesn't have potential adequate current carrying capacity on it. So I know that sounds confusing. Don't worry about it. All you need to know is how to do that first part to determine the conductor's ampacities, or what potentially is going to be on each conductor. And in this case, it looks like one of them, simply a potential of 1 foot difference, okay, in each set. I mean, there's only 1 foot separating each one of these links. That's it. The current exceeds the rating in one set of conductors, okay? Now, look at it this way. Because the impact of conductor's length differences is proportional to the total conductor length, a 1 foot, that's only 3 meters, that's 1 foot difference in individual conductor's length for a 100-foot run would have a significant reduced impact on current carrying differences. Okay? So, that's a big deal. That's why it's so important to keep these links the same. That way the ampacity values are figured out the same. Okay? Now, there is solutions. Don't worry. Don't freak out. Chill. There's a couple ways we could solve this. Okay? Well, the first one is I could pull all these conductors out and reinstall them all at the same length. Okay? And that could get quite costly because a lot of times you'll call us manufacturers and they're going to tell you, nah, we don't want you to reinstall it. Again, of course, you bought the wire, so if you'd like to reinstall it, go for it. But typically, we might say, no. How do we know it's not damaged? And your warranty is for an initial installation. Of course, you bought the wire. You can do whatever you want with it. Okay? But in our case, you might reinstall the wire. And if you want to use the same wire or whatever and try to figure it out, but sadly, the longest length is probably what you need for all of them, and so your other conductors are not going to be long enough. So you'd have to reinstall it. Well, that's one option. You could do that. Okay? I guess the next option you could do if you want to leave things the way they are because they're not the same characteristics and you're worried about how it's going to divide up, I guess you could reduce the overcurrent protection to 1500 amperes. Okay? So how did you do this? Well, they do make 1500 non-standard fuses. Okay? Or I could install a 1600 amp adjustable trip circuit breaker. Okay? And basically, I have a long time setting that I would adjust to 1500 amperes. Okay, I might be able to achieve it that way. But this does not provide the intended 1600 amperes capability. But it does result in no conductor carrying current in excess of the conductor's allowable ampacity. Okay, so and this meets the intent of the NEC in 31015A3. So you do have to check with your local jurisdiction because they might disagree with that analysis, but that is what the code says. You are protecting those conductors at their ampacity. There's also other jurisdictions that will tell you, nope, I want the conductor to be able to carry 1600 amperes. Well, they probably don't know how to parallel anyway, so on the surface, it looks like you do have conductors that can carry enough of the ampacity, because if I took the original value of 420 times 4, that's 1680. So on the surface, they might not have a problem. Now, when somebody like me comes in and I were to see that you didn't think about the different links and you didn't follow paralleling and something happened, I might say, well, now, you had a leg in there that was going to be overloaded. And it's carrying more current than it's designed to carry. So there is options that you can do, but the best option is to understand your installation prior. So if all of my EMTs, for example, are the same length, And when I bring those wires in, I might have to adjust one leg or another by putting a little, not a loop in it, but give you a little slack in order to make sure that all of my conductors are the same length. Now, one way I do it is if I'm going to go to the longest possible length that I'm going to need for my pull. So say it's a 115-foot pull, and I know that that's the longest conductor I'm going to need. And some of the other ones, because of how they're routed in the switchgear or the panel or whatever it is, might be a little smaller. I am going to make sure that I cut all of my conductors to that longest possible length. And then if I have a little extra in there, then I can make a loop out on it. Again, people say, don't do loops. You know what? It's all a preference. Give me a little bit of it that comes out or something like that in order to say that, look, they are all the same length. One might have a little bit more in the actual switchgear than one of the other phases, but who cares? Okay? I just have to make sure that they are in physicality the actual same length. So that's why you want to think about this stuff up front, okay? That makes a huge impact because of how the different lengths are going to have, because of the resistance, are going to affect the actual current that's going to be distributed evenly on it. Now, if they're all the same length, then the current will distribute evenly on those lengths, okay? So keep that in mind. I don't want people to lose the sight of the process of how we came up with the amps and why it's inversely proportional. Just remember, the reason that it switched and now all of a sudden the 20-foot one's carrying the most amps is because it has the less resistance. Okay? So current travels on all available paths. But in reality, it also more current travels on the path that does have the lesser value of resistance. There's less restriction to current flow. So while we do the math to find out what the actual current is based on the length, once we determine that, then it's basically inversely proportional. We flip that, and so in this case, the shortest length is the one that's going to potentially carry the most current. And that's a problem because in that scenario, that is what gave us a conductor that is now carrying more current than it's designed to carry. Now, you couple that with some adjustments and corrections in there, and you got yourself a field day for a current that's potentially going to break down as the heat starts to elevate up in those conductors. Okay? I'm telling you, it's just a real simple steps to do it and find out what the actual, if you have different lengths, that'll tell you. You simply take the length that you have, divide it by your overall accumulated length of all of the runs or all the sets, and then divide that by whatever you're trying to achieve. In this case, it was 1600 amperes. That's going to give you the ampacity based on the length. Now, because of inverse proportionalness to this resistance, obviously you flip them now, and the shortest one is going to carry the most current because it has less resistance to current's flow. Okay, hopefully you get that, and I didn't. It's really hard to depict that in a podcast, but I think you get the concept. I really do think you get it. Okay, all right, that is it, my friends. That is all I want to tell you about paralleling. I'm not going to talk about paralleling in cable trays. We'll leave that for another time. I just want you to fully understand the basic concepts of paralleling raceways. Remember again that MC cables, the equipment grounded conductor that's got to be full sized, is not probably going to be full sized because it's only really designed for that one cable. It was never intended for those MCs to be put in parallel, although you can. It's just you're going to have to account for the issue. Now, that's one of the allowances in cable trays in the 2017. It's going to actually allow you to use MCs with the normal traditional size equipment grounded conductor in that cable, but you're going to have to run a separate full-size one in the cable tray and then connect them electrically like you're paralleling at both ends, and so that it actually is acting like a parallel or in addition to the sizes you have in your MCs. But again, I don't want to confuse anybody. That's for a different topic, a different time. And in fact, I think I also have a podcast on that as well. And might even be a video on it. I'm not sure. But go to our YouTube channel and look for that when it talks about paralleling in cable trays. And I am sure that I know that on my LinkedIn page, I do have an article on it as well. If we're not connected, I should shout out to you. If we're not connected in LinkedIn, go to LinkedIn and search for Paul Abernathy. And you know what I look like. You can click on there and send me a request. Let's connect up on LinkedIn. That's our business network. But again, Thank you for all the listeners to our podcast. Our recent analytics just told us that while I don't do it by subscriber, because on my website, when you listen to podcasts, I don't track subscribers. I track unique listeners by their ISP and things like that. And we have a company that does that through all of the platforms, and we have over 300,000 unique ISP listeners, and we're excited about that. You don't have to subscribe. You can go to our website and listen. Up there, our podcasts, every one of them is updated on there, and you don't have to subscribe to anything. But if you want to subscribe to us, go ahead. But we really don't track the subscriptions. We track the unique ISPs and the footprints that come. So anyway, we have a company that does that for us, and we are excited because we don't pay a lot for it, but the amount of info they give us is amazing. So it's the analytics is an amazing thing. So thanks, everybody. Until next time, stay safe. God bless. And I hope that you visit our website, masterthenec.com. Share it with everybody. Okay? We want you to learn. I do this stuff for free because I want you to learn. Okay? It's not because I like to hear myself, because I don't. I think I sound funny. And I know I look funny. But I love helping people learn. I've dedicated 30 years to it. And I continue, okay, to do so. That's why I write books. That's why I do podcasts. Why I do seminars. All that type of stuff, okay? So, thanks again. If you think you ever get something from these podcasts and videos and you want to donate to these free podcasts and videos, go to our website, go to the bottom, and there's a Donate Now button. You can donate to us to help the cause. We appreciate every donation for everybody out there that we've helped. We'd love you if you want to donate. You don't have to, but if you want to, go for it. Again, thanks, everybody. Till next time, stay safe. God bless.
Every day, the future's getting closer. Every day, the future's looking bright. Every day is another beginning.